Hello students, I am Dr. Varun Mohan from ABES Engineering College, Ghaziabad. This is the first lecture of the lecture series of Unit 3 of Engineering Chemistry, code BS 101 and BS 102. Today we shall discuss about some concepts of electrochemistry. These are the contents of today's lecture. First, we shall define what is electrochemistry and we will discuss some basic terms used in electrochemistry. Then we shall discuss how electrode potential is generated and how is it measured. After that, we shall focus on the construction and reversibility of a standard hydrogen electrode. At the last, we shall focus on electrochemical series, its properties and applications. So let us first define what is electrochemistry. Electrochemistry may be defined as the branch of physical chemistry dealing with the transformation of chemical energy into electrical energy and vice versa. On the slide, we can see three examples of applications of electrochemistry. The first one is an energy storage device, which is called battery. It is frequently used in the inverters, in the automobiles, and also in the electronic gadgets. The second one is an artificial jewelry, which is made by electroplating. Electroplating also works on the principles of electrochemistry. We know when electric current is allowed to pass through an electrolyte, a chemical reaction may happen. This is called electrolysis. Electrolysis also works on the principle of electrochemistry. Now, we shall focus on some basic terms which are frequently used in electrochemistry. Cations. Cations are the positively charged species which move towards cathode in the electrolytic cell. Anions are the negatively charged species which move towards anion in the electrolytic cell. Oxidation is the process of loss of electron, which causes generation of cations. Oxidizing agent are the chemical components which accept the electron and because they are accepting the electron, they get reduced themselves and cause oxidation of the other species in the solution. Reduction is the process of gaining of electron and it generates the anions in the solution. Reducing agents are the chemical components which donate the electron and get themselves oxidized. They cause reduction of the other species present in solution. For example, in this reaction, zinc is losing the electron to form Zn2 plus ions, and copper ions are taking those electrons. So it is converting to the copper in the elemental form. So here zinc is undergoing oxidation but causing reduction of copper 2 plus ions. So it works as the reducing agent. Similarly, copper 2 plus is accepting those electrons from the zinc and it is causing oxidation of zinc. So the copper works as the oxidizing agent for the zinc. A metal rod or plate which is in contact of its own ions is called electrode. It may undergo oxidation or reduction. So electrode may be of two kinds, anode or cathode. Anode is the electrode where oxidation occurs and hence the reactions associated with anode are called oxidation half cell reactions. Cathode is responsible for reduction and hence the reactions associated with cathode are called reduction half cell reaction. Electrolyte is a conductive medium which has cations and anions. It allows the electric current to travel between the two electrodes in the cell. When a metal rod or a plate is dipped in the solution of its own ions, it may undergo oxidation or reduction. The tendency of that metal rod or plate to undergo oxidation or reduction is called the electrode potential. Since each electrode represents the half cell, the electrode potential associated with that electrode is also called the half cell electrode potential. Now we shall see how electrode potential is generated. As we have discussed in the previous slide, the tendency of an electrode to lose or gain electrons is called the electrode potential. When a metal rod is dipped in the solution of its own ions, it may either undergo oxidation or reduction. Suppose this is the zinc rod, which is dipped in the solution of its own ions. Now this zinc rod may undergo oxidation by losing some electrons, and it forms Zn2 plus ions. So zinc 2 plus ions solution, zinc 2 plus ions generated from the metal rod through oxidation ultimately go into the solution, leaving behind the electrons on the metal. Since electrons are accumulated on the metal, it generates a negative charge on the metal. And this negative charge attracts the positive ions from the solution towards it. Hence, a layer of negative and positive charge is developed. And because of accumulation of positive charge here, the metal rod cannot keep on losing the Zn2 plus ions from here. It cannot keep on undergoing oxidation. Hence, an equilibrium is established, and this double layer, which is called Helmholtz electrical double layer, causes the potential to establish between the metal rod and its ions. This potential is called the electrode potential for the oxidation half cell. Similarly, we can consider a copper rod which is dipped in the solution of its own ions. In this case, the copper ions may undergo reduction to form elemental copper. So when these metal ions reach the metal electrode, they undergo reduction by taking up 2 electrons from the metal rod. Hence, it causes a positive charge to be accumulated on the metal electrode. And this positive charge attracts the counter anions from the solution towards it, which generates a layer of negative charge around it. This is called Helmholtz electrical double layer, which causes the potential to establish between the metal electrode and the solution. This potential is called electrode potential for the reduction half cell. So we have seen how electrode potential is generated. Now we shall see how is it measured. The electrode potential can be measured with the help of potentiometer using a reference electrode. The potentiometer measures the difference in the potential between the given electrode and the reference electrode. There are several kinds of reference electrode available, but the most frequently used reference electrode is standard hydrogen electrode. The standard hydrogen electrode has a platinum wire or foil which is coated with the platinum black. It is dipped in the solution of 1 molar H plus ions, and hydrogen gas is constantly bubbled through it at 1 atmospheric pressure. The inert metal platinum here works as a source or sink of the electrons. It works as a catalyst for the reaction, but it does not have any other function. When we have to measure the potential of any electrode, that has to be coupled with the standard hydrogen electrode, and the EMF is measured with the help of potentiometer. Since standard hydrogen electrode is given the potential value of 0 arbitrarily, hence the EMF of the cell gives the potential of the given electrode. The standard hydrogen electrode works as a reversible electrode. It may undergo following reactions. When hydrogen undergoes oxidation to form H plus ions, this is the anodic reaction. On the other hand, the H plus ions may take up electrons to form hydrogen. In this case, reduction is happening, and hence this works as a cathodic reaction. To represent the standard hydrogen electrode, representation is given as platinum hydrogen gas, which is at 1 atmosphere in equilibrium with H plus ions, which are 1 molar in concentration. When a standard hydrogen electrode works as cathode, the other metal should work as anode. An example can be shown as this is the zinc rod. It is connected with the standard hydrogen electrode. So this is SHE. Here the zinc rod works as anode and standard hydrogen electrode works as cathode. Because it undergoes oxidation, electrons are accumulated on it. So this accumulates the negative charge. These electrons move toward the cathode and it is working as the positive electrode. The reactions associated with both electrodes can be shown as at anode, zinc is converted to zinc 2 plus ions and it loses 2 electrons. At cathode, standard hydrogen electrode has H plus ions. So they take up these 2 electrons to form the hydrogen gas. So the net reaction may be shown as these 2 electrons may be cancelled out here. So it is zinc solid in presence of 2 plus ions, 2H plus ions, converts to zinc 2 plus and hydrogen gas is formed. So we can see zinc is undergoing oxidation, so it works as anode, and H plus ions are reduced to hydrogen gas, so it works as cathode. This was about how standard hydrogen electrode works as cathode. But due to its reversibility, standard hydrogen electrode can work as anode also. For example, if any metal may work as cathode, in that case, standard hydrogen electrode may work as anode. Suppose this is the standard hydrogen electrode and this is the copper rod. Here, the standard hydrogen electrode works as the anode and the copper rod works as cathode. The electrons are generated here. These accumulated electrons move towards the cathode, which is having the positive charge because reduction is occurring here. So here it works as anode, the SHE, and copper works as cathode. The reactions associated with both electrodes can be shown as anode, which is the standard hydrogen electrode. Here, oxidation occurs. So hydrogen gas is converting to the H plus ions, giving off 2 electrons. At cathode, copper 2 plus ions in the solution take up these electrons to form elemental copper. The net reaction may be shown as H2 in gaseous form and copper 2 plus ions in aqueous form convert to 2H plus and copper in the elemental form. Here, hydrogen gas is undergoing oxidation. So it is the anode here and copper 2 plus ions are undergoing reduction. So this is the copper electrode is the cathode here. Now about the sign convention of electrode potentials. We know that the Gibbs free energy change and the electrode potential can be shown related to each other by the equation delta G equal to minus NFE, where delta G is the Gibbs free energy change associated with the chemical reaction. N represents the number of electrons associated with the chemical change. F is the Faraday constant and its value is 96500, that is 96,500 coulomb, and E is the potential of the cell. So we can write it here. Delta G is the Gibbs free energy change. N is the number of electrons associated with the chemical reaction. F is the Faraday constant. And E is the EMF of the cell. Under standard conditions, the standard conditions may be defined as 1 atmospheric pressure, 1 molar concentration, and 298 Kelvin temperature. So these are the standard conditions. Under standard conditions, this relationship may be shown as delta G naught equal to minus N F E naught, where delta G naught is the free energy change associated with the chemical reaction under standard conditions, and E naught is the EMF of the cell under standard conditions. We know that delta G naught, if negative, shows the spontaneity of the reaction. So we can show this equation as minus delta G naught equal to NF E naught. So if delta G naught is negative, reaction should be spontaneous. It means if delta G naught is negative, reaction should be spontaneous. But we should remember that if it is negative term, then E should be positive. It means a positive value of E naught shows the spontaneous reaction. Similarly, if delta G naught is positive, it is showing the non-spontaneous reaction. If delta G naught is positive, it means the E should be negative. It means when E naught value is negative, it represents the non-spontaneity of the reaction. And when delta G is equal to 0, it shows the reaction is in equilibrium. And delta G is 0, it can happen only when E is 0. So the 0 value of E naught represents the chemical reactions are not happening or the cell is on cell is in the equilibrium state. Now we shall see how do we represent a reaction. Generally, in electrochemistry, all the reactions are represented as the reduction reaction, and the potential associated with them is shown as the reduction potential. For example, this is a reaction in which zinc is undergoing oxidation, losing some electrons, and the oxidation potential associated with it is 0.762 volt. So this reaction can be shown as a reduction reaction by reversing the reactants and the products and the sign of the potential. So to represent this reaction as a reduction reaction, we can show it as zinc ions in contact with two electrons convert to zinc solid, and the potential here should be given the reverse sign having the same magnitude. So that is 0.762 volt. This is how we show a reaction as the reduction reaction, and the potential here will be called as the reduction potential. Similarly, for this reaction, where iron is converting into iron 2 plus, it is undergoing oxidation by losing 2 electrons. It can be shown as the reduction reaction as and the potential here should be given as minus 0.447 volt. So here this reaction is converted to the reduction reaction, and the potential here shown as the reduction potential. Once all the reactions are converted, those are shown as the reduction potential. It is easier for us to compare them and to arrange them in the increasing order of the reduction potential. So when we arrange them in the increasing order of reduction potential, such a series is developed. This is called electrochemical series. So electrochemical series may be defined as a series in which the elements or the ions are arranged in the increasing order of their standard reduction potential. From this series, we can observe few things. The first one is that hydrogen is given as the zero reduction potential as discussed in the slide of standard hydrogen electrode. This is given a zero reduction potential arbitrarily. Next thing which we observe is that most of the metal ions are listed on top of the standard hydrogen electrode. These have standard reduction potential values lesser than the hydrogen electrode. Third thing we can see is that most of the non-metallic elements like sulfur, iodine, bromine, chlorine, fluorine, these are listed at the bottom, which are below the standard hydrogen electrode. They have the reduction potential greater than that of standard hydrogen electrode. We can see as we move down the series, the atoms are stronger in the oxidizing power. But as we move upside in the series, the elements are stronger in the reducing power. So from the series, we can see lithium is the strongest reducing agent and fluorine is the strongest oxidizing agent. But this electrochemical series has a few limitations also, like the first one is that the electrochemical series has the potential which are determined only under the standard conditions. It means 1 molar concentration, 1 atmospheric pressure, and 298 Kelvin temperature. These are the standard conditions. So these potential values can be used only when the standard conditions are applied, when we are doing the chemical reaction under standard condition. Second limitation of electrochemical series is that it does not tell about how fast the reaction will happen. Means it does not tell about the rate of the reaction. Despite having these two limitations, electrochemical series finds numerous applications in the chemistry. The first is comparison of oxidizing and reducing power. As we have discussed in the previous slide, the elements listed on top have highest reducing power and elements listed at the bottom have highest oxidizing power. It means it is easier to compare their reducing or oxidizing power if we have electrochemical series with us. Prediction of displacement reactions. The electrochemical series helps us to predict the displacement reactions. Any metal which is higher in the electrochemical series can reduce the metal which is below the element under consideration in the electrochemical series. It means any metal listed above can displace any other metal listed below from its salt solution. The ability of metal to liberate hydrogen gas from acid. Electrochemical series can help us to predict which metals will liberate hydrogen gas from the acid. Any metal which is listed above the standard hydrogen electrode has the tendency to reduce the hydrogen ions to the hydrogen gas. It means any metal which is listed above the standard hydrogen electrode will give the electrons to the H plus ions and convert it to the hydrogen gas. It means the metals on top of the standard hydrogen electrode can displace the hydrogen gas, those can liberate the hydrogen gas from the acid. Calculation of EMF of the cell. With the help of electrochemical cell, we can calculate the EMF. With the help of this electrochemical series, we can calculate With the help of electrochemical series, we can calculate the EMF of the cell. Prediction of feasibility of the redox reaction. We know that spontaneity of the reaction can be determined with the help of the Gibbs free energy change. If E value is positive, the delta G value will be negative and the reaction will be spontaneous. So we can predict the feasibility of the redox reaction with the help of calculation of EMF. If E is positive, then the reaction will be feasible. Now let us see a few questions which are asked in the previous years. What is the electrochemical series? What is the potential of half cell consisting of zinc electrode in 0.01 molar zinc sulfate solution at 25 degrees centigrade? E naught value is given. The first part of this question, what is electrochemical series, has already been discussed in this slide. So electrochemical series is the arrangement of different elements according to their increasing standard potential. Second question, give important applications of electrochemical series. This also we have discussed in the previous slide. Applications of electrochemical series include comparison of oxidizing and reducing power, prediction of displacement reactions, ability of metal to liberate hydrogen gas from acid, calculation of EMF of the cell, and prediction of feasibility of the redox reaction. So today we discussed about few concepts of electrochemistry, standard hydrogen electrode, its applications, and the electrochemical series, its properties and its application. These are some of the references. In the next session, we will discuss more details about the cell construction and we shall derive Nernst equation. Thank you for attending this session.